Mm. So, good afternoon, everyone. My name is Paola Buitrago. I'm the PI of Neocortex and Director of AI and Big Data in the Pittsburgh Supercomputing Center. I'm also co-PI of the ByteBoost Cyber Training Program. And it is my pleasure to welcome you to the Neocortex webinar as part of the ByteBoost Cyber Training Program. So today we will be talking about everything about Neocortex. Of course, it's an introduction because we will only have 1 hour. But then with me, you also hear from Dana O'Connor, machine learning research scientist in the AI and Big Data group at PSC, and also Julian Uran, machine learning research engineer, who will be facilitating the hands-on portion of this session. So without further ado, let's just dive right into it. But we'll some maybe rules of our session today. So as mentioned over email, right, and in previous webinars, this webinar will also be recording. We expect to make the recording and slides available in the ByteBoost Google Classroom. If you don't have yet access to the Google Classroom, please let us know. You should have an email with instructions, but if you don't find instructions, or if there's any question, to let us know through a message here in the Zoom chat, or by sending an email to the program email address, which is byboost25@ecchair.org, I believe. We can confirm that. Second, you are all invited to submit an application for our in-person workshop that we will be hosting in Pittsburgh. It will be hosted by the Pittsburgh Supercomputing Center. The applications are accepted until April 27th. So we are encouraging you all to participate and apply. The application is very lightweight, so a statement of research and optionally an abstract or a proposed capstone project. If you have any specific project that you want to run in any of the platforms or the testbed platforms that we have discussed in ByteBoost, do mention that. That would be an excellent application and would increase your chances of getting accepted for the in-person workshop. And today for this session, we expect to have 20-25 minutes of presentation, right? An overview of Neocortex. And after that, we will have a quick tutorial that will last about half an hour. And we will conclude with 5 minutes of Q&A. So we ask you to please keep your microphone muted during the presentations. If you have any specific question, please use the Zoom chat feature, share the questions there. If we can address them offline, as a response to your message in the chat, that will be a first way of approaching it. Otherwise, we will address the question in the 5 minutes after the presentation and hands-on portion of the session. Something to keep in mind is that this webinar abides by the Neocortex Code of Conduct. So just regular standard rules, right, to make sure that our session and this space is conducive to learning and everybody feels welcome and can express their ideas well. Here is the link for the Neocortex Code of Conduct if you want to go read in more detail. And please contact me or Sergio or other Neocortex PI for any sort of guidance or assistance you may need on this front. Now, let's talk a little bit about the Pittsburgh Supercomputing Center. This is the supercomputing center that houses Neocortex. PSC, as we normally refer to the Pittsburgh Supercomputing Center, was established in 1986. It's a joint effort of the University of Pittsburgh and Carnegie Mellon University. And it's a national supercomputing center, so we are focused on offering advanced computing resources, hardware, networking, storage, compute, networking, and storage, and also expert support to open science being advanced in any kind of academic institution in the United States. So areas of expertise includes HPC and data-intensive computing, data management technologies, software architecture, implementation, and optimization, and just anything that has to do with enabling groundbreaking science and computer science and engineering. So PSC is mostly funded or by the NSF and NIH, and also has collaborations with the private sector. So if you have a startup or know of a startup or a company that also would like to collaborate with the PSC, we're happy to get on a conversation or get on a call. Now, let's talk specifically about Neocortex. So Neocortex is a project that was proposed in response to solicitation 19587 by the NSF, and it's a category 2 type of system. That means it's an innovative prototype or testbed. So it's the award of Neocortex is OAC 200-5597, and the official title is Unlocking Interactive AI Development for Rapidly Evolving Research. Neocortex is delivered in collaboration with Cerebras and Hewlett-Packard Enterprise. And it basically looks like what we have in the image, right? So it's a system that offers specifically an HP Superdome Flex. So that's a very powerful server on its own, and that has 24 terabytes of RAM. That in itself is a amazing spec. So not only, so if you have an algorithm or some kind of scientific compute that requires a lot of memory, right? So it's memory intensive. That would be a good candidate maybe to specifically use the HP Superdome Flex. So besides the 24 terabytes of RAM, there are 32 Intel Xeon CPUs. We have in total 204.8 terabits of NVMe SSD. That's also very large storage, and all of that in a single node. Now, as mentioned, the Superdome Flex in itself is a very powerful node, and for most of you might be already what can serve your compute and memory needs. But besides the HP Superdome Flex, what we have in Neocortex is also two Cerebras CS2 servers, with each of them hosting one Cerebras wafer scale engine. That's one of the most innovative elements of Neocortex. As mentioned, Neocortex is a testbed, and one of the main missions is to test this wafer scale engine and server offered by Cerebras. So the wafer scale engine is featured here in the picture on the right. It's a very large chip that was specifically designed to vastly accelerate AI training. So it has 850,000 cores that are optimized for sparse linear algebra. So all those matrix multiplication and operations that are very much needed when we are talking about neural networks. It has 2.6 trillion transistors. It has 40 gigabytes of on-chip memory. That means memory that is one clock distance from the compute elements. So it's a very, very, very powerful resource on its own. So in Neocortex, basically what we have is the Superdome Flex, which, as we mentioned, has amazing features. And then the Superdome Flex is tightly coupled with two Cerebras CS2s. So the communication between the Superdome Flex and the Cerebras CS2s is 1.2 terabits per second. That's very fast, because what we have in each of the Cerebras nodes is a very powerful, fast AI chip that you need to feed rapidly. Otherwise, if you don't feed it, if you don't feed the training data fast enough, basically you're starving the accelerator. Now, what we can see here in the bottom of the diagram on the left is that a Neocortex is integrated at the data level with Bridges 2. So Bridges 2 is another supercomputer that we make available through the Pittsburgh Supercomputing Center, or is made available by PSC. And from Neocortex, we can leverage the file system Ocean, which is around 15 petabytes of storage. And also we have the JET file system, which is NVMe SSD, so it's faster. This is kind of to see how the architecture looks like in the demo. Julian will show us how do we interact with each of these components, right? So how do we get access to Neocortex? How do we submit a job and get one of these CS machines going with the training of a specific neural network of our choice. Now, what we are seeing right now is the original version of the Neocortex, and what we continue to offer. Something that we have recently made available to Neocortex is access to a CS3 unit, which is the latest generation of the Cerebras server and features a wafer scale engine 3. It's an enhanced version of the wafer scale engine. The wafer is the same size, but there is additional compute cores, larger on-chip memory. So all in all, a way more powerful system. Also, it is integrated with other elements that Cerebras has developed since the original proposal that we are defined Neocortex. So it works with SwarmX and MemoryX, which are two elements that Cerebras leverages to use different type of parallelism. So in that case, pipeline parallelism. Some of you might be familiar with the fact that you can parallelize AI training at the data level, model level, and then there's also pipeline parallelism and other approaches. So this specific opportunity to access the CS3 is available for selected projects. So please pay close attention to Dana's part of the presentation. Well, she will describe what the specific functionality is made available through the wafer scale engine 3. And if there's something that catches your attention, do reach out to neocortex@psc.edu or reach out to any of us directly if you have a model or a project that you believe would be a great fit to CS3. We will be happy to jump on a call and explore that further. So this is visually how the Neocortex system looks like. If you join us in August, we expect to have a machine room tour, so you most likely will get to explore and learn more about the Bridges 2 system, given that it's also integrated with Neocortex, and also the Neocortex system. It has a rack, and as you guys can see here, we have 1 and 2 units. Then the the Super Flex is this black rack on the right in the center image. What are some of the advantages of using Neocortex, right? So Neocortex, we just have what would be an alternative to the NVIDIA GPU, right? So instead of using the NVIDIA GPU or, well, AMD GPU or other kind of GPUs, you would be leveraging what is the wafer scale engine by Cerebras. Here are some performance benchmarks that have been prepared by our team in the Pittsburgh Supercomputing Center, so in particular by Dr. Miyu Wang, who couldn't join us today because at the same time we normally host office hours, right? So Wednesdays at 2 p.m. Eastern time, there are Neocortex office hours that all of you are welcome to join. But what we can see here is the comparison with a BERT large network and also Camberta MLM pre-training. And we see the performance if we are comparing B100s by NVIDIA, A100s, and the Neocortex wafer scale engine 2, and the wafer scale engine 3, and the ALCF. This one would be deployment of the wafer scale engine 2 in Argonne National Lab. So as what we have in the y-axis, the vertical axis is it's powers of 10, right? So the baseline is 10 to the power of 2, then 10 to the power of 3, and 10 to the power of 4. So it's orders of magnitude larger for specific networks. So as we can see, right, with Neocortex, it certainly does perform way better with when you're talking about one accelerator, and when compared to the A100s and B100s. We will be enhancing this data to include also H100s. And we see that between the deployment in the cloud, or well, the wafer scale engine 3 and the ANL deployment and our deployment, sometimes the sometimes the cloud, the wafer scale engine 3 performs better, sometimes the wafer scale engine 2. And that is because of the system architecture and also the use of all these other elements that I mentioned enable different types of parallelism. If you're curious about these results and want to learn more, we also encourage you to get in contact. And these are, for example, some type of projects that we can explore as part of ByteBoost, right? Comparing different accelerators, not only those that are in Neocortex, but also those available, let's say, in ACES and other testbed systems funded by the National Science Foundation. One example of a success story or one excellent scientific outcome that Neocortex has made available involves a scientific workflow that, as a matter of fact, doesn't use AI. This is a workflow that is computational fluid dynamics. It was advanced by the National Energy Technology Laboratory in collaboration with Cerebras and PSC. And it basically allow the simulation of convection in a single Cerebras CS2 servers with a level of resolution and at a speed that was completely unprecedented. And when compared to the outcomes that you would get with a supercomputer, being well, considering that you could run this whole simulation in the single chip and everything was one clock away, that really enable this great outcome. Like the level of resolution and speed was completely unseen at the time. So this is already from last year, but since then there have been further simulations of interest. To give a sense of who is running right now on Neocortex, because Neocortex has been around now for 3 years and we are currently in our production phase. So these are the fields of science of or what domains do projects that currently run on Neocortex, what fields they come from. So there's a lot of artificial intelligence, and well, what is classified as computer science, so that would be also sort of artificial intelligence. But we also have projects from biological sciences, engineering, physics and astronomy, medical engineering, economics and business, mathematics, geophysics and geochemistry, and chemical science. So as of December of last year, we had close to 50 active projects. If you want to learn more about the kind of projects that are currently running on Neocortex, we invite you to visit the project webpage, right? So neocortex.psc.edu, and there is a button there where you can see what are the current projects that are running. And I believe we also have a list of former projects that had at some point used Neocortex. So with that, we'll have now Dr. Dana O'Connor, tell us a little bit more about the type of applications that are supported on Neocortex.
Yeah, sure. Thank you, Paola. So, like Paola said, my name is Dana, and I'm a machine learning research scientist here. So, here are what we call the four tracks of Neocortex. So, these are the types of applications we support. So, track one is going to be models that are already coded up and ready to go within what Cerebras calls their model zoo. So, these include models such as BERT, a few variations of GPT, Linformer, Roberta, T5, as well as a vanilla transformer model. You can also code up multi-layered perceptrons as well as 2D UNet. So the software stacks that are supported are TensorFlow and PyTorch, as illustrated here. And you can use the allowed layers from TensorFlow and PyTorch of the Cerebras software stack to move on to track two, which are machine learning models similar to the Cerebras model zoo models. So if you want to like swap out a activation function for another or create your own custom layer, or even code your own models from scratch using these supported layers within TensorFlow and PyTorch, it's totally possible to do that under track two. Track two can also include, swapping out data sets for models that already exist in the model zoo. But you, like I said, can also code your own models using the supported software. Track three is a little different. It's general purpose SDK. So if you want functionality that is not supported in the current software stack, you will have to write your own custom kernels in the SDK. And then you may be able to use those new functionalities. And then the fourth track is domain-specific programming. So it is the waiver scale engine field equation API, which is how we were doing those computational fluid dynamics simulations that we saw a couple of slides ago. So this involves having a problem of partial differential equations discretized to first and second order in implicit or explicit methods. And they fit really well on structured grids. So you need to make sure that your problem has one of those grid setups. So these are our four tracks. And when you apply for an allocation on Neocortex, you will have to specify which track you plan to follow. Next slide. All right, so a bit more detail about the four tracks. So we'll first go over topics 1 and 2. So these are basically using the models within the model zoo with few changes or using the supported layers within the model zoo to build your own models. So Neocortex is best suited for running transformer style models such as BERT, GPT, Transformer T5, and VIT. Transformer style models, as I'm sure we've all heard, cover a range of tasks. This includes sequence classification, sequence annotation and generation, as well as sequence to sequence mapping and representation learning for biological sequences. And then we have some example projects that you can go through below. Next slide, please. And then we also, as Paola said, have access to a CS3. This CS3 not only comes with new hardware, but also a newer version of Cerebrus's software stack, which actually has a expanded version of the model zoo. So whereas we saw a couple of the transformer style models that the CS2 at Neocortex supports within the cloud with the CS3, we get access to not only BERT, Roberta, Transformer, GPT, and T5, but these models here as well, including 3 versions of Llama of several different sizes, as well as Mistral and ESM2. And then Cerebrus has recently proven that, or displayed that they have the fastest inference in the world on several of these models, including DeepSeek, which you can get access to through the Cerebrus API inference. So there are a lot of models available within both Neocortex as well as the CS3 that we have access to in the cloud, and they're both really good for inference as well as training. Next slide. Yeah, so here's an example of a deep learning application. So this is Camberta, which is Roberta trained on millions or at least hundreds of thousands of text representations of molecules that are called SMILE strings. And this is usually a pre-training task that is then used for further downstream training on prediction or classification tasks. And there's been quite a bit of work using Camberta for these different tasks. And this is actually very easy to train on Neocortex. It only takes a couple of hours to train 10 million SMILE strings for a couple of epochs, as opposed to several hours or maybe even days on traditional GPU architectures. Next slide. Yeah, so if you are looking to port your model to Neocortex, it's not a model that you see is available already in the model zoo. This is the general process that you're going to want to follow. So first, you want to build your layers within the model function that will come within the model Python script. You then want to reformat your input data function in the data.py script. And then you'll want to implement any helpers that you need in utils, and then customize your parameters within the configuration files. And then before you train the model, you'll want to run.py to validate and compile your code. So this will just tell you if you have any easily detectable errors that will prevent you from running your code on Neocortex. So then here's also a schematic of how that works. The run.py script takes from the configurations of where to find your data as well as your utils. They use that to then build out the model, and then they use their own custom TensorFlow runner to actually train the model. Next slide, please. Yeah, so we follow a similar workflow for PyTorch. So there is a class that Cerebrus has implemented of a base model for PyTorch running on the CS2. You then read the input data in with data loaders that interface with PyTorch. Again, implement any helpers you need in utils, customize our parameters within those configuration files, and then again, run, validate, and compile to make sure that your model is actually going to run on the CS2. And then we see the workflow here is a little different. We take the configurations and then generate a training data loader and an evaluation data loader at the same time as creating our model and then wrapping that around the PyTorch base model. So we first start off by building a model the normal way with the nn.module and then wrap it in this base model class. And then the run function is carried out on the Cerebrus base model as well as the training and evaluation data loaders. Next slide. Yeah, so for the SDK, the CS2 essentially appears as a big array of 150,000 individually programmable processing elements. So this is really good for really large simulations, which is another application of Neocortex, is these traditional HPC simulations that fill up large grids. And the benefits and features of this is that we have high bandwidth and low latency, as well as 40 gigabytes of on-chip SRAM. And then some topics of interest for the SDK include structured grid-based PDE and ODE solvers, dense linear algebra, as well as sparse linear algebra, Monte Carlo simulations, as well as custom machine learning kernels. Next slide, please. And then here is our last track, which is the wafer scale engine field equation API. So this is pretty domain specific. This is solving spatial temporal problems on structured grids. This is proven to be several hundred times faster than distributed computing, so over multiple GPUs or CPUs. And this has a simple NumPy-like Python front end, and you can see the documentation here. And like we said previously, you have to be able to lay this problem out on a grid, so a 3D or many 2D parallel. It should involve some spatial locality, so the neighbor interacting with its neighbor. It should be data intense, and then we support single precision, less than 40 gigabytes, since that's the amount of SRAM. Some examples include computational fluid dynamics, structural mechanics, geomechanics, weather and climate, as well as some materials modeling, such as the icing model and density functional theory. And then we can also implement convolutional neural and recurrent neural network inferences. Next slide, please. All right, so to learn more and participate, you can go to the sites. So the ByteBoost program is listed here. For the Access program, we have that as well. So Access is the way that we are giving you access to all of these resources. It's an NSF-funded ecosystem that connects you to all of these NSF-funded resources, not just the Pittsburgh supercomputer or UCAMI or ACES. It connects you to all of the resources that are available there free of charge to academic researchers. So we encourage you to learn more about that here. If you are interested in applying to the NAIR pilot as well, which is a National Artificial Intelligence Research resource, you can apply there. The NAIR pilot has more specific calls than Access. Access is just justifying why you need some computer time, and it's really simple to get a small allocation through Access. The NAIR pilot is going to be much more specific, and it is going to require a lot more planning because it's very similar to like actually writing a full proposal for something like the NSF. And again, the call is a bit more specific. They're looking for specific applications in artificial intelligence, but if you'd like to learn more, we encourage you to go to that link. And then we also have the Neocortex documentation, which will pretty much have all of the information that we covered here today spread out over a couple of pages. And you can go there if you need a refresher on any of the things that we covered today. And then, of course, if you need any help, please email us at neocortex@psc.edu. Next slide. All right, I think I'm going to hand it over to Julian, who is our machine learning research engineer for the FC-MNIST tutorial.
Thank you very much. Appreciate it. All right, so thank you everyone for being here. The idea with this tutorial is that we're gonna have a hands-on example using a fully connected MNIST code. And so the idea is for you to click this documentation link, the Neocortex documentation that I'm just gonna paste here in the chat window, for you to go to our documentation and be able to follow the getting started tutorial. So this is what you should see on your end. Please let me know if anyone has any issues following this part. So some information that was sent yesterday is that the idea is to double check access to the Neocortex Open On Demand portal, because that is what we are going to use. So the idea is that we're gonna log in into the portal and we're gonna start up a Jupyter notebook to be able to follow the tutorial. So now let's click this link for getting to the Neocortex Open On Demand page and authenticate with your PSC username and password. So the idea is that you have an assigned PSC username and a password. So if you got to double check it before getting here, that's great. If you don't, or if you don't have access to those, please let us know and we can also help you figure it out. But then there is additional information here in case you don't know your PSC username, or in case you don't know your password, so you can just reset it using a simple web page. So please follow these steps at your own pace for being able to get into Open On Demand. All right, so the tutorial, as I was mentioning, it's a hands-on FC MNIST that will get you started using the system. So following this tutorial, we will be able to get into Open On Demand, launch a Jupyter Notebook, and then interact with the different components there to be able to train a model on the CES, on the CDRS hardware. So we're going to be using a fully connected neural network model, and then the data set that we're going to use is MNIST, that is a collection of handwritten digits. We are going to use some training parameters from the base configurations that we have for the example. I just did a table here for you to be able to take a look at those. And also there's here like the set of important URLs to have in mind when following this tutorial. So in case you need to reset your password, in case you need to go to the access allocations portal to double check your username, link for getting to Open On Demand, and link to get to the actual getting started tutorial. So the first step is after you log in, um, is to, just give me one moment, I'm logging in here, is to launch Jupyter Notebook. So you should click that application in the middle. So Jupyter Notebook, you click it, you specify a couple of parameters that are already documented here in the same documentation page. So you should just request like 1 hour that we're gonna last here, or two, just a single node. And then for the Slurm arguments, please input like dash dash account equals, and then the charging account that we're gonna use for this. We're using for ByteBoost. Everything else can be left blank, and then you just click the blue button that says launch. As soon as you do that part, you will get into this screen that says that this Jupyter Notebook server is queued, and then after that it says running. And
One
then
second, Julian. Maybe shall we ask the attendees how many of them have followed along and like where they are? Like, okay.
the password reset should be almost right away. So you click send me a link, you get the email right away. If not, please double check your spam folder. And then you use that code to put it into the form, and it's automatic. Mm,
Thank you all of those, for those of you who have confirmed that you're following along. Martin, as Julian said, I resetted my password this morning and it was automatic, right? So I reset it. It does send you a code to your email address. And after you provide the code in the password resetting tool, then you change the password and then you should be good to use it right away. Or that was my experience this very morning. If you're still having issues, please let me know so we can get you in contact with other members of our group. Now, yeah, I sent in the chat account equals TRA. That's the account that we should be using when instantiating the Jupyter Notebook, right? So as Julian showed, can you go back to the Jupyter Notebook screen, Julian?
Yes, so you click
Sure.
it here.
So number of hours, we're gonna select 1, the number of nodes 1, and in extra Slurm arguments, you can just copy paste exactly the message that I sent a couple minutes ago, right? So minus minus account equals then TRA 25009, well, 09P. If anybody is having any kind of problem, please do send a message in the chat, and both Dana and I are available to help, as well as Julian, although he will be facilitating. Or raise your hand and we can help you. Now,
All right, sounds good.
yeah, now something I want to say, right, like to keep in mind, is that you all will continue to have access to Neocortex with this allocation for 1 month more past this webinar, right? So it's great if you manage to complete all the steps that Julian will describe in one moment, but if for some reason, let's say your account is not ready or something, and we need to take extra steps outside outside of the webinar, we'll be happy to assist you, and then you can try on your own and also get additional help by the Neocortex team. So with that, Julian, I'll let you go continue with the tutorial. Thank you.
All right. Okay, so we were here in which the Jupyter Notebook says it's running already. So I'm just gonna click this connect to Jupyter button, and then that's about it. Then the next step is after we get to that point, because here are the screenshots of the Jupyter Notebook running, and so the next step is to uh, open up a terminal. So from Jupyter Notebook, click the upper right corner where it says new to open up a terminal. So I'm just gonna click it here. It says new terminal. And then copy this command. We're just gonna download the actual Jupyter Notebook file that we're gonna use. So just a simple wget command that I just executed. And so it just downloaded the file here, getting started IPython notebook. Please let me know if someone is having issues running the command, and I'll help you. All right, and then the next step. Just give me one moment. I'm just gonna rename this because it got a wrong name. So it should be IPython notebook, the extension. So I'm just gonna start it up here. So I'm just gonna click the file, and it will bring me to this screen. What is the link to open up Jupyter app? So if you go to the first section, like the home page, or if you click open on demand, it will show you Jupyter Notebook there in the middle. So the idea is for you to click this one, the one that has orange. So if you cannot access open on demand, then you will not be able to get to this screen. The link, give me one moment. So the main link for the tutorial is this one, and then that has like all of the different information. And then for getting to the Neocortex Open on Demand portal, this is the link that we just used. All right, so you will be in this screen. So at this point, we will be good to start the actual tutorial. So please feel free to follow at your own pace. The idea, as it was already mentioned, is that you have access for about a month. So it has all of the information in a self-contained way for you to be able to perform the training. This information that we have here is what we already mentioned regarding the model being used, the data set being used, and the parameters that we have here. And then we are reviewing once again the different tracks that Dr. O'Connor already talked about. So since there are different tracks, let me just mention that this example that we're running here, FCMNIST, um, fully connected MNIST, is part of track one because this is part of the CDFRS model SU ML models that come by default. So if you want to take a look at the other models that are available there, you will find this one in them. And then for being able to run the tutorial, the idea is that, of course, you need a PAC account. You just need to be able to run this IPython notebook, and then the MNIST dataset will be automatically downloaded, same as the CDFRS model. So you, as soon as you get here, you will be all set. The steps that we're gonna run is that we're gonna set some helper variables to be able to run the different steps of the job in a more automated way. So we can just click. Then the code itself will clone the model zoo repository that has the example. That will be track one. And then we're gonna navigate that folder to the fcmnist directory, and then we're gonna run a couple of commands. So we're gonna validate that code with a validated command. Then we're gonna compile it, and then we're gonna train the actual model with the dataset. Is everyone following along? Let us know if you have any problems.
There are
All
a
right,
couple
so
questions, Julian, in the chat. And well, I'm trying to address them like with messages and instructions, but yes, so maybe if you can illustrate how to get a terminal going from the open on-demand environment. Like,
yes, of course. So the idea is that you go to the Open On Demand webpage and you have a couple of options for opening up the terminal. Maybe the easiest one is here in the main screen. You just click this one on the left. Well, it says it was terminated, so let's try with the second one. So as soon as you start Jupyter Notebook, you get like something here showing on the upper right, so new, and then it's showing there as terminal. This screenshot is also available here in the documentation page in case you want to take a look at it. So it's this one here. So the idea is that you start Jupyter Notebook using the icon in the middle, the one that has orange, like Jupyter Notebook, and then you get to this screen after clicking the launch button, and then you can just click like new, and here in the upper right, new button, and then at the bottom you see like terminal highlighted with the arrow. All right, so that's how you get the terminal, and then you just switch to the previous tab that you had, select the IPython notebook you download with the wget command, and at that point you will get back here to this Jupyter notebook file. For the two images, well, it seems like something broke during the. Yeah, you don't need to double check the IPython notebook on GitHub. You can just download it. It's not rendering the view correctly in GitHub. We have to dig deeper as to why is that happening. And then for the images that seem to be broken, those are these images that are shown in the documentation page. So if you want to take a look at those are just visual representations of fully connected neural network and then MNIST handwritten digits. So it's those are not required for following along in the tutorial. Now for the first step, we're gonna set some helper variables. The idea here is that we're just automating the launching of the of the jobs here in our Slurm cluster. And so we're gonna set some some base paths, for example, what development environment we're gonna use, and then what arguments are we gonna use with Slurm to launch all of the different jobs. So we're just gonna click run on this one, and that's about it. So we'll just run some code, and that's it. Then we're gonna clone the GitHub repository. So that GitHub repository is this one, Model Zoo from CDRS. And then at the same time, this is the latest and greatest. We have tag 160. So the idea is that we're gonna run these steps for cloning the repository and then checking out the specific tag that we need. So just gonna click run, and then it's now cloning the repository. It just finished, and then now it's in the specific branch that we need for our firmware, the one that is compatible. Are you being to clone the repository? Please let me know if you run into any issues. All right, so we have that the head is at R160, that is the expected output, and then we're gonna run step 3, that is an ls for being able to take a look at the files that were checked out for that revision, and we shall have a set of files like these ones. So these files are the ones that are powering the Model Zoo example that we're gonna go through. So we have a set of different files and directories. The important part is that you have, for example, run.py there, and also model.py, data.py. You should have like a couple of data.py and of Python files, and then the configs directory. For each of these different files, there's a set section, a role that they have when running the code. So when you need to configure, for example, the location of your dataset or the number of epochs that you're gonna run through, or the batch size or things like that, you should edit the params file, any params file under the configs directory. That will make it easier to keep everything contained. It's a YAML file, so you just set the values that you need as required. Then for the data file, this is the file that includes the data pipeline definition. And so everything related to data processing will be contained in this file, and then you just will import it from somewhere else. Then for model, it will have the model definition, so the different layers that it has, and all of the other functionality that is bundled there. Then rumpy, it contains this set of scripts, I mean the arguments for being able to start the different scripts that we're going to run. So there is a workflow for running validate, a compilation and trainings, but all of those, like those three, you access through the run.py file. So in the end, when you interact and you want to run compilation evaluation, you just run with run.py, and that will take care of editing of invoking like the data.py, and then that at the same time will also take a look at the params file to get all of the data as required. So in general, what we usually will use for making sure that our data is being used for training is that we're gonna edit the params.file to make sure that we're loading our data set. Then we're gonna modify data.py as needed for adjusting it to our data set. We will be able to reuse the rest of the files. So run.py will call model and whatever you configure in data and params, and you will be all set. So yeah, basically configure these two, and you will be able to customize it for your specific workflow. Now, for the different steps that I have been mentioning, so we have a validation step, compilation step, and a training step. The idea with validate is that it will double check that everything is fine, that everything is supported by the Cerebra's software stack. And so the idea is to first run this validation step. Then after that, we will compile the code to get it ready for then going into the training step and actually running it on the CS machine. The first two steps, validate and, compilation, those run in CPU and like in the Superdome Flex that is driving the training, like all of the execution. And then the training step, this one actually takes place between both the SDF that streams all of the data into the CS machine, but the actual computing, like the computation heavy, it takes place in the CS machine. And now let's take a look at the example. So for this first step, for validating, step number 4, I mean, we're gonna run a command in Slurm that will basically invoke Python for run.py, and it's gonna say like dash dash mode train with the validate only argument. And then this other argument, model dir, will output all of the different results from that, all of the validation results into this folder called tutorial model dir. So I'm just gonna run this. It just got assigned as a job ID in our Slurm queue. And then it's gonna run as soon as possible. So let me just double check how the queue is doing at this time. I see that a lot of you already started the job. So let's just give it a moment. So in this case, since it's running on CPU, we don't have to wait much. And then it starts by downloading the MNIST dataset. That is the output that we see here. And then it starts like generating the training examples, followed by generating the test examples. So let's just give it a minute until it finishes. At the end of the output, you should notice that this changes into a number because it will have been completed, and then it will have something here at the end as well saying that the job, the compilation, well, the validation in this case completed, and then um, the job is finished. So we just finished this one. At this point, we can say that all of the different code that we have here from the repository is compatible with the Cerebra software stack that we're using for validating it. So everything looks good. Now for the next command, we're gonna compile the code. So about the same arguments are going to be used, only that one of them was changed for compile only. So it's going to be still like dash dash mode train, and then we're still using the same model directory that is reusing the values from the previous step, the validation one, but then now we're doing the compilation part. So I'm just gonna run it here. Same as before, it allocated a job into our Slurm cluster and it will start processing. And then as soon as this part finishes, we will get to the actual training. So it's about the same set of steps, but now we don't use that part, the compilation or the validation flags. We just use the mode train and we specify a variable for connecting to the CS IP address, like the CS2 machine IP address, and then it will show an output similar to this one in which it started the training. It took a look at the graph and then it went through the different steps for being able to train the model. As soon as that part finishes, you will have like compilation completed. And then finally, um, you can also take a look at the contents of the folders and the files that are there inside the tutorial model there. The idea is that there is, for example, the total utilization of the wafer that you are expected to use with this specific example. This one is 1.7%. That is fine because it's just a small model for a getting start tutorial. So the utilization is low, but then the idea is for you to optimize it for your specific scenario and make the most out of the chip available. Well, any questions?
Hi, maybe I'll ask a question with respect to the allocation on the Cerebras machine. So I'm wondering, so you only use 1% of it, right? Is it possible to split it between multiple jobs, the single chip, kind of like NVIDIA's MIG, or something like that?
So for this specific version of the Cerebras hardware, only one job is expected to run on the Cerebras CS2 machine at a time. So the idea will be for you to be able to make the most out of the chip and then just run it like one job at a time. So if you can get that to 100% total utilization, that will be great, but only one job at a time.
So yeah, just to complement, so the chips do not support multi-tenancy, right? So only one job runs at a time. And then, as Julian mentioned, right here, we are running MNIS with a fully connected network that is more for training and educational purposes. But a good use of this chip is to have very large language models running, transformer type architectures that would have a higher utilization of the chip.
Yeah, sure. Did I understand right that you just have two of these, or the Neocortex has two of the chips? Is that correct, or
That
more?
is correct. So there are two in our data center, and then for special projects, right, we can have access to the Cerebras cloud to and get access to one of their CS3 machines.
So
Now,
yeah,
go
what's the likelihood of me say my job starting within reasonable time then? Or do you have reservation for this workshop or what?
We can, well, we don't have a reservation for this workshop, right? Like the jobs normally run very fast, right?
Okay.
Because the chips are super fast. And well, here, I guess was defining also the length of the job is how many uh, epochs or steps we are assigning. And I know Julian selected 10,000. So that's what made it last longer. But for the training of a network like this one, it will complete in less than 1 minute. Or it will be seconds. So the ideal scenario is when we have researchers, as I mentioned, like really making good use of the chip with very large neural networks, or there are data needs, right, that really call for the chip to be used. So thanks, Martin, for the questions. I see that we are at the top of the hour. Now I know, Julian, maybe can you project those slides? There are some slides that and final message that Dana will
Do you
be.
see the slides?
Yeah.
All right, yeah. Thank you, Julian, for that great demonstration. So here we want to just wrap up with our call to action. So you'll have 1 month after today to run the examples shared in the webinars, so to play around a bit with FC-MNIST. Please take the quiz available on the Google Classroom. It has been published, so it should be ready to go. Quizzes are mandatory if you are going to attend our in-person workshop. Slides and recordings will also be made available in the Google Classroom as soon as possible. We also wanted to tell you how to get help with Neocortex. So you can join the office hours. We have open office hours every Wednesday at 2 p.m. Eastern Time, or you can request a 30-minute session with a PSC expert via this scheduling app called Calendly. And then you can also participate in our in-person ByteBoost workshop hosted by the Pittsburgh Supercomputing Center from August 4th to August 8th of 2025. 25 people will be selected, and you can read more about how to apply on the ByteBoost website. And we are accepting submissions until April 27th. So you need a statement of research interests as well as an optional abstract of a proposed capstone project you want to complete during the workshop. Next slide. Yeah, so we'll just, we are pretty much out of time, so we'll just go over these quiz questions really quickly. So the first question is, what are the main compute resources available in Neocortex? A hint here is that Neocortex does not have GPUs, so choose wisely. And then that kind of feeds into which of the following GPU acceleration frameworks are available on the Neocortex system. Pretty good hint that we don't have GPUs. Next slide. Which of the following tracks is not one of the supported tracks? So remember that the chip that we're working with is called the Cerebrus wafer scale engine here, and that the collection of models is known as the model zoo. And then remember that we also talked about that fourth track of domain-specific applications. And then for question 4, remember that this chip is really big, so you might want to pick a big number. Next slide. And then what Neocortex track does the hands-on example correspond to? This is also pretty explanatory. I think it might even say it in the tutorial, but remember that we did not really alter any of the code within the Model Zoo example. And then in the hands-on examples, what files would need to be modified in order to use a different data set. I believe that this also might be detailed in the tutorial, but think about what we would have to change if we wanted to use a different data set. Will we have to have configurations pointing to different directories? And would we have to maybe call a TensorFlow datasets library to download a different data set? So that is going to be the quiz. So I think that wraps up this webinar from ByteBoost covering Neocortex. Paola, is there anything else you wanted to say?
Nothing else to add. Thank you, Dana. Thank you, Julian. Thank you all for joining. And we invite you to complete the tutorial and also the quiz. If you couldn't complete the tutorial right now, like as mentioned, you'll have access to the allocation for 30 more days. So any question that you may have, please do not hesitate to contact the team at neocortex@psc.edu. And once again, the slides and video will be available through the Google Classroom. So thank you all and have a good rest of your day.